So back to problem 2.6. In the previous video, we found an expression for the numerator. And here you can see I've continued the calculations a little bit. So you can kind of check your own calculations up against what we have here. The numerator should evaluate to 25.96 or something like that. So now let us try to take a look at the denominator, the probability that x lies between 10 and 100. So let's take a look at that. We want to look at the probability that x lies between 10 and 100. And in this case, since x is continuous, well, this is also equal to the probability that x is strictly greater than 10, smaller than 100. Which is equal to the probability that x is strictly greater than 10 and less than equal to 100. And this part of the equality is because x is continuous. Okay, and what we have here is that this expression is actually equal to the probability that x is smaller than equal to 100 minus the probability that x is smaller than equal to 10. And what's the reason for that? Well, we want to look at the probability that x lies between 10 and 100, right? We want to look at this part. So if we want to find that, we can take the probability that x is smaller than 100 and then minus the probability that x is smaller than 10, because then what we're left with is the probability that x lies in this interval. In order to find this, we need to find the distribution function of x and evaluate it in 10 and in 100. Now, when x is exponentially distributed, its distribution function is of a special form. So let us do that just completely in general, also so that you have this formula for later. I also think it actually turns up in one of the later chapters, but it's also good to go through the calculations here, so let's do that. So, in general, if x is continuously distributed, so if x is a continuous random variable, then the distribution function of x is given by the integral of the density from minus infinity all the way up to x. So if x is exponentially distributed with parameter lambda, then its distribution function is given by the integral from minus infinity to x of the exponential density, which we recall looks like this. So it's lambda multiplied by e to the minus lambda x. Here we have the 0.01 because I've already substituted in the values. But for the general case with any lambda greater than 0, the density of an exponentially distributed random variable is given by lambda multiplied by e to the minus lambda x. And also recall the important detail that x has to be greater than 0, or else the density is just 0. So when we evaluate this integral here, well, we have the density lambda multiplied by e to the minus lambda y dy. And here we write y because it's y we integrate with respect to. We integrate all the way up to x. But we have to think a little bit about what we put down here, because the density is greater than 0 only when y exceeds 0. So if x is exponentially distributed, then for x greater than 0, we have that the distribution function is defined as such. Now what if x is smaller than 0? Well, then the distribution function is just 0, right? Because then we just integrate the density from minus infinity up to something that's smaller than 0, and we just integrate 0. So it's only the case x greater than 0 that's interesting for us. Now let's try to evaluate this. This is equal to, take the constant outside of the integral, the antiderivative of this thing here is minus lambda multiplied by e. No, it's not. It's minus 1 over lambda and then multiplied by e to the minus lambda y, where we have the upper bound x and the lower bound 0. So what I have here is lambda over lambda, that's just equal to 1. And then I have e to the minus lambda 0 minus e to minus lambda x. And I just removed the minus sign here by switching the order of these two. So this works pretty well. And what I have is 1 multiplied by e to the 0, which is 1, minus e to the minus lambda x. So this thing here is equal to the distribution function of x when we look at values little x greater than 0. Now, how does this help us with solving our problem? We want to find the probability that x lies between 10 and 100, and that is equal to the distribution function in 100 minus the distribution function in 10, which is equal to, now we just use what we have here, it is equal to 1 minus e to the minus lambda x, and our lambda is 0.01 multiplied by 100. And then minus 1 minus e to the minus 0.01 multiplied by 10. The two ones, they cancel. We have a minus minus, that's a plus. So we have e to the minus 0.01 multiplied by 10 minus e to the minus 0.01 multiplied by 100. And that's something like e to the minus 0.1 minus e to the minus 1 to the minus first. So this is the denominator, and the numerator was 25.96. And all in all, we want to find the mean of x given that x lies between 10 and 100. So in conclusion, the mean of x given that it lies between 10 and 100 is given by the fraction where the denominator is the probability of the conditioned event, and that is e to the minus 0.1 minus e to the minus first, and where the numerator is given by the mean of x restricted to the event, to the set that I used to construct the event I condition on, and this mean value has 25.96. Plug that into a calculator and you get 48.34. So as expected, given the knowledge that the claim size is between 10 and 100, so strictly less than 100, we do get a mean value that is somewhere between 10 and 100, compared to if we only knew that x was exponentially distributed and it could attain any value between 0 and infinity, then we would have thought that the mean was equal to 100. So it kind of helps to condition sometimes. If you have any extra knowledge, then put it into the part where you condition.